Hi everyone, I'm Mikhail. Welcome to the Dark Wire YouTube channel where we break down network technologies and bring them to life with real code. In today's video, we are exploring the NAT hole punching technique. As always, we'll wrap things up by writing some practical code to see it in action. Let's get started. First, let's recap what NAT actually is. NAT stands for Network Address Translation. One of its primary purposes is to allow multiple hosts on a private network to share a single public IPv4 address. This technology essentially saved the internet from exhaustion of IPv4 addresses. You might also hear it referred to as source NAT, since the source IP is translated from private to public for outgoing traffic, or port address translation. Nowadays, it's everywhere from home and enterprise networks to Internet of Things devices. By default, clients behind the source net can initiate outgoing connections, but they cannot receive incoming ones. If you want a client with a private IP to be reachable from the internet, you typically need a different type of net static mapping, via IP or port forwarding. However, in the modern world, not all communication is client to server. We rely heavily on peer-to-peer communications for things like remote access, like TeamViewer or AnyDesk, audio and video calls, peer-to-peer gaming, BitTorrent, and others. SourceNAT creates significant barrier for these services. That's where NAT hole punching comes in. What is NAT hole punching? NAT hole punching is a technique that enables two hosts both behind NAT to establish a direct connection without manual port forwarding. It's primarily used with UDP because UDP is connectionless. The NAT state is created as soon as the first outbound packet is sent. Let's look at the three main scenarios for peer-to-peer communication. First scenario is both peers have public IPs. No NAT traversal is required. A direct communication works every time, unless a firewall explicitly blocks it. Second scenario, one peer behind NAT, one public. The peer behind the NAT initiates the connection to create the NAT state. This is the simplest traversal case and almost always succeeds. Third scenario, both peers behind NAT. This is a classical hole punching challenge. Success here depends heavily on two NAT behaviors, mapping and filtering. Mapping means how the NAT assigns ports, and filtering means which incoming packets the NAT allows to through. Let's talk about basic workflow of hole punching. First step is discovery. Both peers contact a public meeting point server, often called a STUN server. Second step is observation. The server identifies the public IP and port mapping for each peer. Third step is exchange. The server shares this public endpoints with both peers. Fourth step, the punch. Both peers simultaneously send packets directly to each other's public IP and port. Next step, state creation. These outgoing packets punch a hole in each respective NAT, creating state entries that allow return traffic. And final state, direct connection. A peer-to-peer link is established. From this point on, the server is no longer needed, it's only for coordination, not for data transfer. Let's now review NAT mapping types. The first type is endpoint-independent mapping, where the external port does not depend on destination. NAT in device will try to retain the same source port when translating private IP to a public IP. This type works well with hole punching. It's common in home routers. Second type is endpoint-dependent mapping, also known as symmetric NAT. The mapping changes per destination, often using port randomization, so you can hardly guess the port. This usually breaks basic hole punching, because the peer sends to the wrong port. It's common in carrier-grade NAT, mobile networks, and enterprise firewalls. Even if mapping is stable, inbound packets may be filtered, so we also need to consider NAT filtering types. There is endpoint-independent filtering, so called full cone. Any external host may send to the map port. And second type is address-dependent filtering. Only hosts previously contacted may send back. Third type is port-restricted filtering. Only the exact IP and port previously contacted may send back. That's the most restricted one. Hole punching works when mapping is endpoint independent and both peers send packets to each other to satisfy filtering rules. And that's exactly the scenario we are implementing in today's video. As usually, I used some help from AI to generate code for me. I've got a server code, which is meeting point, the public server, and the client code. It's written in Python. I use Visual Studio Code to run it. The client code, I'll run it on my local machine. And the server code, I'll run it on a virtual machine in a public cloud, which is accessible through a public IP address without NAT. Okay. So first, let's take a look at the server code. So that's the server code. It's pretty simple. The server is listening on UDP port 9999. And what it does, once it receives a packet from a client, it registers this client. So in the console, it writes the client ID and its public IP address. And the public ID, client ID, sorry, that's the identifier which the client will send. And as soon as we get two clients registered, the server will exchange their IP address details and the port details with each other. Yeah, and it will report in the logs peers exchanged. That's it. As for the client code, so the client, it connects to the public IP of the server. That's public IP address of my virtual machine. This client is using ID 2. Yeah, it will send UDP packet to the server, so the server will register it. And then it will learn from the server the peer information. And once learned, once registered, it will start the punching phase where it will continuously be sending packets, multiple packets to the other peer, trying to make a hole in NAT. And after a while, and we set a timer for that, it will send hello to the client, expecting also to receive hello from the other end, from the other peer. But obviously for this example, I need the second peer. And I have a Linux device located actually in another country. I have remote access to this device. So what I did, I asked the AI to write similar code for the client, but in this case to write a C code So I compiled it for that machine. It's actually ARM CPU architecture. I compile it, I copied it to that machine, and I'll run this program from that machine. And I also need to copy the server code to my virtual machine with the server. So that's my server. As you see, I've got this Python code, and I'm going to run it. Now I'm running my other client, which is in the Linux box. So it's also connected to the same server, and you see immediately the server received packet from it. That's the public IP address, and that's the source port, how the server sees it. Now let me go back to the Visual Studio Code and run my second peer. Sorry, sometimes I call it client, sometimes I call it peer. Of course, that's the demonstration of the peer-to-peer communication, but the file is named client in terms of its communication with the server only. So please don't get confused by this. So as you see, as soon as I ran it, sorry, and I need to move it here, it got registered and it started receiving hellos from the other peer, from peer 1, and also it's sending hellos. And my other peer is also receiving hellos. Here in the server logs we see that the second client is registered with this IP and this public port. Lastly, let me run packet capture. I'm going to specify the port of the first client. Okay, you see these are hello messages. So this is the message coming from the client 1 to my local machine where client 2 is located. Let's take a look at the port. The source port is 36290. Yeah, and the destination port is 57923. So both of these ports were discovered by the server while these two peers contacted the server. This is working only because my routers on both the sides, they actually doing endpoint independent mapping, and they are retaining the same source port that is being used by the peers. So for example, this peer, my local machine, that's my local IP address, it's sending packets from source port 57923, and this port is retained. Also, when it contacted the server using the same port, the port is retained. If my home router was doing port randomization, then this example would not work. There could be some techniques to predict the actual port, but it doesn't work well. So it really depends on actual scenario. Okay. I hope you enjoyed this video. See you soon.